Welcome to this explainer. Today, we're doing something pretty cool. We're taking the high-level goals of the newly updated physics curriculum and smashing them right into the gritty, practical reality of measurement errors. We're going to look at exactly how this shift in educational standards directly impacts what you do at the laboratory bench. All right, so here's our game plan. We've got a clear roadmap designed to take you from those macro-level educational standards right down to the micro-level physics. We'll hit the new curriculum, the foundation of measurement, categorizing those unavoidable imperfections, diving into the math of mistakes, and wrapping up with how to minimize errors to absolutely maximize your results.
Let's jump right into Section 1, the new physics curriculum. We start by looking at the overarching framework for the senior secondary school transition. It's a really crucial phase, marking a big shift from general education to a highly rigorous, discipline-based focus for the 2025 to 2026 academic year. Now, what's actually really interesting about this updated syllabus is its explicit shift. It's moving away from simple memorization and heavily toward genuine process skills and international standards. They're reducing the load by eliminating overlapping concepts, logically sequencing the topics, and leaning heavily into SI units and standard nomenclature. It's really all about promoting your ability to apply knowledge and solve problems rather than just rote repetition.
So the core mission here, it is crystal clear. To develop the investigatory skills that you will actually use out there in real scientific environments. You're meant to be exposed to the actual processes used in physics-related industrial and tech applications. It's about building a rock-solid conceptual competence so you can really appreciate how physics interfaces with other disciplines. Which brings us nicely to Section 2, the foundation of measurement. Listen, if we're going to be doing all this experimental and observational work, we have to start with how we actually measure the world around us. And the very first step here is acknowledging kind of a chaotic reality. Literally, no measurement is perfectly accurate. Measurements are the absolute foundation of scientific experiments, but errors, they are strictly unavoidable. This deviation from the true value is exactly what we define as an error. And, since the true value is often a mystery, we have to rely on repeated measurements just to even estimate it. Moving on to Section 3, categorizing imperfection. Because these errors are completely unavoidable in any lab setting, we've got to learn to categorize them based on where they come from. You have to understand where a mistake originates to have any hope of fixing it. There's a very distinct line between our two main culprits here. On one side, we've got systematic errors. These are consistent, predictable flaws caused by your instrument or your method. On the flip side, we have random errors. These occur unpredictably and irregularly. A classic example? Imagine a sudden fluctuation in your voltage supply while you're taking an electrical reading. You can't predict it, but boom, it completely skews your data. Okay, let's break down those systematic errors a bit further, because it's crazy how easily minor factors can throw off your data. Instrument errors come from bad construction, calibration issues, or even a zero error built right into the tool itself. Then you have observation errors, usually from an improper setup. Think of the classic parallax error, right? That happens when your eye isn't perfectly aligned with the scale. And finally, environmental errors. This is when conditions like temperature, pressure, or air resistance completely interfere with your setup. And of course, we have gross errors. These are basically just the very human mistakes that completely wreck your measurement map. We're talking generally large errors caused by sheer carelessness. Writing down the wrong number, grabbing the completely wrong instrument entirely, or just misreading a clearly marked scale. We've all been there. All right, Section 4, the math of mistakes. Identifying an error conceptually is great and all, but this is physics. We must actually quantify it. Calculating the absolute error is super straightforward. It's simply the difference between your measured value and the true value. And, by definition, it is always expressed as a positive number. To put that into a real-world perspective, say you're measuring the length of a rod. Your measured value is 20.5 centimeters, but the actual true length is exactly 20.0 centimeters. You just subtract the true value from the measured value, leaving an absolute difference of exactly 0.5 centimeters. It's really that simple. But here's the catch. What happens when you use those measurements in a larger equation? Well, errors compound. It's like a snowball effect. When a result is calculated from two or more measured quantities, the errors combine depending on the math operation. For addition or subtraction, the absolute errors simply add up. But check this out. Notice how the mathematical rule shifts entirely when you move to multiplication or division? There, it's the relative errors that combine. And if a quantity is raised to a power, the error is multiplied directly by that power. So mistakes don't just add up, they multiply. Literally. Let's bring it all home in Section 5, minimizing practical errors. We need to connect these theoretical math calculations directly back to your academic performance and the syllabus standards we talked about earlier. Your practical evaluation requires you to submit a rigorous record of at least 8 experiments and 6 activities. And here's the kicker. Maintaining this record, including your precise observations and your error handling, directly accounts for 5 solid marks out of your total practical score. Furthermore, the syllabus mandates an investigatory project. Executing this project with high precision, maintaining proper error calculations, and demonstrating true experimental manipulation, that secures you another 3 absolutely crucial marks. So the big takeaway here is that mastering measurement errors isn't just a theoretical exercise. It is literally the foundation of maximizing your entire 30-mark practical evaluation scheme. Between your 2 main experiments, your practical record, your activity, your investigatory project, and your viva, every single one of those 30 marks relies heavily on your ability to measure accurately and handle those inevitable errors correctly. Now, while you can never fully eliminate errors, utilizing a few actionable steps will drastically minimize them and seriously elevate your scientific process. First, use instruments with higher precision. Always take your readings exactly at eye level to avoid that pesky parallax error. Ensure your tools are properly calibrated before you even start. And most importantly, repeat your measurements, take the average, and whenever possible, perform your experiments in highly controlled environments. We're going to wrap up this explainer with a final thought, just to spark your curiosity. We've established today that error is a constant, unshakable reality of the physical world. So, in a universe full of unavoidable physical imperfections, what is the acceptable threshold of scientific truth? How precise do our instruments really need to get before we can finally say we've measured the universe exactly as it is? Something to chew on next time you step up to the laboratory bench.